Now you can start. Please switch on the camera. Some of you haven't switched on the camera. And leave it switched on until 9:35. OK。第一次补考的有很多吗？第一次。都是第一次，那你就告诉你，我们就调一个时间，也是25分钟，然后给他们第二次没有，第二次只有他们就是那个9:35，这一次的其实也可以安排一个时间，就是跟那个一起的，对，那我给你2个，就安排这个星期或是下个星期一个星期，一起。这个晚上也可以的，就是因为反正那个比较单纯，可以全部都是网络的。
Okay, so time is over. Please upload it. We make a break of 10 minutes. Please take a picture and upload it to Moodle. For some of the students doing the quiz online, you should maybe next time you should reposition your camera, because some of you, I only see the top of your head. So you should position the camera such that at least the table is also visible, and actually you are visible and the table. We'll continue at 9:40. explained last time, the derivative of a function, I write as a special limit, namely the limit h tends to 0 of f of x plus h minus f of x divided by h. Or equivalent way of writing this is the limit x tends to a tends to x minus f of x divided by t minus x. You get this form by this form just by change of variable. You say that h is t minus x. So t is then x plus h, and you get this one. So that's the so-called derivative of a function. We also saw already why we are interested in this limit. We saw two reasons. The first one was this is the slope of the tangent of f at the point x. This was the first reason. So if you want to compute the slope of a tangent, or if you want to solve this tangent problem, you are naturally led to this limit. I explained this last time. The second interpretation of this was in physics. An important concept is the instantaneous rate of change. And the derivative gives you the instantaneous rate of change of the function f at x. So for instance, if f describes the movement of a particle or the movement of a car, then you are often interested in the instantaneous rate of change, which is just the velocity. So in this case, the derivative is just the velocity. And of course, you can keep on doing this. You can, because this is now a new function, and you can ask what is the derivative of the derivative. Okay, and in terms of the rate of change, what you are asking for is the rate of change of a rate of change, also considered in physics. If you consider the derivative of the velocity, you get the acceleration, and so on. So these are so-called higher derivatives. But so far we haven't discussed, if I give you a function, how to compute the derivative in a systematic way. Of course, you can always write down this limit. You can try to evaluate it. That's always one way to compute it. But since derivatives are so important, that's not a very efficient way to compute derivatives. So today we wanna start with chapter 3 in the textbook. In this chapter, we are going to systematically study how to compute derivatives. And we will use a similar approach as for limits. So the reason why we were able to compute complicated limits was because of the limit laws. And we figured out the limit of easy functions. So for limits, basically, if you have a function, what we did is if the function is very complicated, we break it into pieces. We solve the limit problem for the pieces. And then we have rules, the limit laws, how to glue together the pieces. And the same approach we are going to use here. So for instance, if you have a polynomial, of degree n. So that's a polynomial of degree n. Now if you want to compute the derivative of the polynomial, of course you can just plug it in here and do the computation. But here you only have to figure out, okay, how to handle this the constants, how to handle power functions, and then how to handle, and that this will eventually allow you to differentiate any polynomial. So we are first. So let's first take the most easiest function, a constant function, the function which is constant c. This is a constant. Of course, here the graph is so easy that from the graph you immediately see what the derivative is, because clearly the slope of the tangent to any point of this function is 0, because it's just a horizontal line. You can also easily verify it by the definition. So you compute the limit h tends to 0. Now the function is just c. This is also c. So c minus c divided by h. That's clearly 0. Okay. So the first function, the first rule which we memorize is that the derivative of a constant function is 0. Now next, how about the function f of x is equal to x? Again, you can just use the so the graph of this function is very simple. It's just a line of slope 45 degrees passing through the origin. So clearly you see that the derivative must be equal to 1, because the slope, the tangent in any point is just the line itself, and the slope is equal to 1. Now, similar, you can use the formula to compute. If you use the formula, you will get that the derivative of f of x is equal to 2x. Then you can try x to the cube. Again, if you use the definition, you will quickly see that the derivative is equal to 3x squared. Okay, so now you can guess the pattern. Namely, the derivative of x to the n is equal to n x to the n minus 1 for all n, for all natural numbers n. Actually, also includes 0, because for 0, this function is just 1. The derivative of 1 is indeed 0, as you have here. Now, I haven't proved this, because these are just some special cases which I checked. So in order to prove this, again, you just use the definition. So the derivative of x to the n, this is by definition the limit h tends to 0, then x plus h to the n minus x to the n divided by h. Now the only thing you need is, because you have to expand this, this will be a polynomial in x of degree n. You have to expand it. And for expanding this, in high school or junior high school, I don't know where, you have learned the so-called Binomial Theorem. So if you expand this, then you have a term a to the n plus, then you have a term a to the n minus 1, b. And there is some coefficient. And then you have a term a to the n minus 2, b squared. And again, there is some coefficient, and so on. And the last one is p to the n. Now, you have learned the Binomial Theorem, which tells you what the coefficients are. The coefficients are just what are called the binomial coefficients. Usually denoted by this notation. Maybe in high school you use this one. I don't know. This is not very common in mathematics. This one is the common one. And you know how to compute the coefficients, right? So you start with 1, then you have here 1, 1, 1, 2, 1, and then you always add. You write the 1 at the beginning, you add those 2. Then those 2, 1, and so on. 1, 4, 6, 4, 1. It's called Pascal Triangle. And what you see here, if you count the rows, so this is the zeroth row. This is the first one, second, third. That's exactly the n. N is the row number, and k is the entry in the row. So this is what you have to write here. These are the coefficients. So here you write. This is in English we read n choose k. So this is n choose 1. This is n choose 2, and so on. This is n choose 1. This is n choose 2, and so on. Actually, there is a more convenient way of writing this. I don't know whether you have seen this in high school. We usually use the sigma sum, then k from 0 to n, then n choose k. This is the coefficient, and the term is always a to the k, or a. The way I wrote it is b to the k. Right? The exponent of a is decreasing. The exponent of b is increasing. So that's called the binomial theorem. And this one. So this is the limit h tends to 0. And then here I expand it. So it's the sum k from 0 to n. N choose k. Then x to the n minus k. H to the k. Minus x to the n. Divided by h. Now you see, if you choose here k is equal to 0, then the binomial coefficient is 1, because you are just here. So this one is 1. Here you have x to the n. Here you have also 1. So the term for k is equal to 0 cancels with this one, because it's x to the n. So in fact, I can remove this one, and then the sum just goes from 1 to n. H tends to 0, then the sum k from 1 to n, x to the n minus k, h to the k, divided by h. And now you see here, these are the terms of the sum. So this means just summing up those terms. Since k is now always larger or equal than 1, this means each term has at least one h. So you can divide by h. Each term you can divide by h. And then you get the h tends to 0. The sum k from 1 to n. N choose k. X to the n minus k. And then h to the k minus 1. Polynomial, because k is larger or equal than 1. So this is just a polynomial in h. And if you x, you can x, everything else is just parameter. It's a polynomial in h, because you consider h tends to 0. The limit is in h. If you have a polynomial, you get the limit just by plugging in h is equal to 0. If you do this, then there is only one term left here, namely the one for k is equal to 1, because that's the only one. That's the only term where you don't have h. H is 1 in this case. So what you get is n choose 1, x to the n minus 1, which is indeed n x to the n minus 1, as I wanted to prove. So this shows this result. So that's the end of the proof. You can say it's just a simple computation. Actually, you can ask here whether this is true as well if n is replaced not if n is not only a positive integer, but if n is any real number. For instance, if f of x is equal to square root of x, you can directly, again using the definition, you can compute the derivative. I'm not going to do this; it's an easy computation. Or maybe it's good to see it, so I quickly do it. So it's we last time we computed limits like this. So here the trick is slightly different. Not you if n is a positive integer, we use the binomial theorem. Here you cannot use the binomial theorem. So here you use a different trick. You multiply with this term and you divide by it. Then you see that if you multiply this out, you see that this becomes x plus h minus x, which is h, and cancels with this one. So what is left is then just this term. And now computing the limit by the limit laws, you get this as answer. And you see, indeed, this is 1/2, x to the minus 1/2. So this means this rule is also, because this is x to the 1/2. You see, this rule is also true for n is equal to 1/2, which is not included in this case. Now you can try more examples. You can try x third root of x, which is x to the 1/3. Slightly more complicated now to compute this. But again, you will see that same rule holds. So it's replaced by any real number. The rule is still the power rule is still true. Okay, but the proof you just saw for this case doesn't work in the general case, right? Because the proof was based on the binomial theorem, and the binomial theorem you just have for integers, positive integers. So the proof doesn't work. So later on, that you can indeed extend the power rule to exponents n, which are any real number. Later on. Not yet, because we don't have any rule yet. We can only case by case use the definition of the derivative and compute the corresponding limit, like here. It's not important for us at the moment because we want to find the derivative of polynomials. So in fact, the textbook calls this the general form of the power rule. So in fact, you have that the derivative of x to the n is equal to n x to the n minus 1 for any real powers n. So for instance, if f of x is equal to x times square root of x, then you can write this as a power, so it's x to the 3/2. So you see that the derivative is 3/2 x to the 1/2. Okay, by this general form of the power rule. You can, for instance, for this example, you can try it directly using the definition. Okay, we'll see. evaluating the limit, you need a kind of the same trick as I used for the square root. Okay, so now we can differentiate powers. So we can differentiate constant functions. Okay, but how to differentiate polynomials? So for this we need to figure out what is the derivative of c times a function. Okay, because this function we can do it. A constant times a function. We need a rule for it, and then we need a rule for the sum, the derivative of the sum. I will prove this general form of the power rule later. For this we need another method, the so-called method of implicit differentiation, to prove this. So now the next result is if f is differentiable, then the derivative of a constant times f is just okay. This once I have this will allow me now to differentiate not only x to the n but an times x to the n. The proof of this is also very simple. Just by the definition of the derivative. So the derivative of a constant times f, let's write f of x, of this new function built from f of x is the limit h tends to 0. Now a constant times f of x plus h minus a constant times f of x divided by h. And now because of limit laws you can just take out the c. So this is c times the limit h tends to 0, f of x plus h minus f of x divided by h. But that's just by definition c times the derivative of f of x. That's what I wanted to prove. So now we can differentiate all these terms and so on. Also the last one we can differentiate because we know how to differentiate a constant function. So the last piece which we need is if f is differentiable and g is differentiable, how about the sum, f plus g? There is a similar result which says that if f and g are differentiable, then the derivative of the sum, so also the sum is differentiable, and the derivative of the sum is just the sum of the derivative. Easy. So if you have the derivative of the sum, by definition, this is the limit h tends to 0, f of x plus h minus g of x plus h minus f of x minus g of x divided by h. Now you only have to suitably rearrange it. So this is f of x plus h minus f of x divided by h plus, and then g of x plus h minus g of x divided by h. Now we know that this limit exists by assumption because f is differentiable. We know that this limit exists by the assumption. So we can use the limit laws. The limit of a sum is the sum of the limits if the individual limits all exist, which is the case here by assumption. So you can write the limits here and here. Here you can write the limit. And if you do this, so actually you can write this now. Sorry, I don't have enough space, so I write it like this. That's just the limit law. And now this is the derivative of f. This is the derivative of g. So you get the derivative of f of x plus the derivative of g of x. Okay, that's the proof of this. And now using this rule here, using the rule for a function, a constant times a function, and using the sum rule, we can now differentiate any polynomial. Before I do this, actually from this sum rule, from this rule for the sum, you can find already some consequences. The first one, if you have three functions, and you want to differentiate it, then it's just again the difference of the sum. It's just by iteration this rule. By iterating this rule, you consider this as a function plus this one, then you apply it once, and then you apply it once more to this function. And the same if you have the sum of n functions. The derivative of a sum of n functions is the sum of the n derivatives. And another consequence, which already follows from this one and from the rule that the derivative of a constant times f is c times the derivative of f. You get that if you have a derivative, if you have a difference, this already, you don't have to prove this now once again, because you can write this as f of x plus and then minus 1 times g of x. And then you apply here the sum rule, and then the minus you can take in front of the derivative. So in fact you get now that the derivative of a difference is the difference of the derivatives. Already a consequence. Okay, so the polynomial which I showed you last time when I introduced derivatives was this one. So you see now the derivative is just 3x squared minus 1. And if you differentiate this once more, so the second derivative is 6x. And the third derivative is 6. And then all the other derivatives are 0 for all n larger or equal than 4. Okay, so that's one example. So polynomials we can now differentiate. We can also differentiate slightly more complicated functions. For instance, find the tangent parallel the tangent of, actually it's 2. The tangent to the function y is equal to x square root of x, which is parallel to the line y is equal to 1 plus 3x. So this means we have to find the tangent which has also slope 3, because it has to be parallel to this one. So y is equal to, I can write this as x to the 3/2. So the derivative is 3/2 x to the 1/2. Now we have to find the point where the slope is equal to 3, because that's where the tangent will be parallel to this line. So if you solve this, you see x is equal to 4. And then if you plug it in, you see that y is equal to 8. So the equation of the tangent is y is equal to, the slope is equal to 3. So it's 3 times x minus, the x value is 4 plus 8. So the tangent is 3x minus 4. That's the tangent to, that's the only tangent to this function which is parallel to this line. Okay, so power functions we can now differentiate, and also all polynomials we can differentiate. I mean, we can differentiate them without having to go to the definition of the derivative. Now, how about exponential functions? So let's say I have the function a to the x. A is larger than 0, any real number. So is this function differentiable? And if yes, what is the derivative? So the derivative, we don't have any law yet for this function, so we just have to go back to the definition. So it's the limit h tends to 0, a to the x plus h minus a to the x divided by h. You see that the limit just depends on h. So I can take out here a to the x. I can write this as limit h tends to 0, a to the x, and then a to the h minus 1 divided by h. And this here doesn't depend on h, so I can take it in front of the limit. Okay, so this will be a to the x limit h tends to 0, a to the h minus 1 divided by h. So I'm left with computing this limit. Note that this is the derivative of the function at 0. So this means, what I just did means this function is differentiable for all x, if and only if it's differentiable at 0. I only have to figure out whether it's differentiable at 0 or not in order to know that this function is differentiable for any x. This is what this relation says. Because this limit, I don't know yet whether the limit exists or not. Also, we don't have any limit laws. And using our definition of e to the x is would be a little bit awkward, because we defined a to the x by the graph, saying we fill the holes, whatever that's supposed to mean. Okay. From this, it's a little bit hard to. Of course, you can plot it, but if you zoom in to 0, no matter there might be something strange, but you haven't zoomed in wide enough. Try now for certain values of a, you can try numerically. You take this limit and you study it numerically. So for instance, for a is equal to 2, if you have this limit, h tends to 0, 2 to the h minus 1 divided by h. You can try to study it numerically, taking h smaller and smaller. You will see this should be roughly 0.69 if you study it numerically. So it seems if you pick different values of a, this limit seems to exist for any a. Okay, but we don't have a proof yet. We will prove it later. Again, we need some other laws for this. There is only one special case where we actually know what this limit is, namely a is equal to e. Because for a is equal to e, you remember how we defined e? We defined e as the base a such that the slope of the tangent to a to the x at 0 is equal to 1. Okay, so e is actually defined as the number where the limit h tends to 0, e to the h minus 1 over h is equal to 1. That was our definition of of e. That's I defined this in the first lecture. Maybe you agree now that this is a very weird definition, because we don't know yet whether the limit even exists. Okay, so it's strange to define something via something we don't know whether it exists or not. Because that was our definition of e. But if we accept this as definition and plug it in here, then we see at least for we know what the derivative is. It's just e to the x. That makes it very special, because if you have here, if you replace a by 2, if you have 2 to the x, then the derivative of 2 to the x is not 2 to the x, it's 2 to the x multiplied with some number, namely this number here, 0.69 and so on. So e to the x is the only one of the, it will turn out to be the only one of the exponential functions which has the property that the derivative is the function itself. That makes it rather special. That's maybe one explanation why it's called the natural number. Okay, but so far the only function we can, the only exponential function we can really differentiate is e to the x. So that's another differentiation rule. I will come back to a to the x for any a later. For this I need the chain rule. But now we can do, if we have a function involving e to the x, we can also usually differentiate it. For instance, we can now differentiate e to the x plus 1 minus x, for instance, this function. Because the derivative you can write this e to the x. This is e times e to the x. So if you differentiate this, you have the e doesn't matter. It's just a constant. And the derivative of e to the x is e to the x. And minus the derivative of the difference is the difference of the derivatives. So minus, and the derivative of x is 1. So the derivative is e to the x plus 1 minus 1. Okay. Okay, so what is the next step? The next step is to look at a product of two functions. So what is the derivative of the product? If I multiply two functions, then differentiate it. What is the rule? Now the first case would be the derivative, the product of the derivatives. That's maybe the first case. Now, but you can easily find functions which show you that this is wrong. For instance, if you choose f of x is equal to x, g of x. Actually, very easy case is g of x equal to 1. Okay. Then you see that the derivative of the product, that's just 1. It's not equal to the derivative of x times the derivative of 1, because this would be 0. Okay, so it's not that simple. So we have to look at the definition, and then to figure out what is the derivative of the product. Okay, so the derivative of a product, by definition, this is the limit h tends to 0, x plus h, g of x plus h, minus f of divided by h. I eventually want that I want to rewrite this such that eventually I have the derivative of f and the derivative of g inside. The derivative of f by definition is the same limit, but you don't have g. The derivative of g is also the same limit, but you don't have the f. These are the things you want to have inside. You want to rewrite the limit such that you have the derivative of f and the derivative of g inside. Right? So how do you achieve this? Now, if you think a little bit about it, maybe you come up with the idea, okay, I want to have the derivative of g inside, so maybe I need the f of x. The derivative of f, so I need the f of x. So I want to have something like this here. Okay, but I don't have this term. So I subtract it and then I add it again. And here you have minus f of x, g of x, divided by h. Now I rearrange it in a suitable way. So this is the limit h tends to 0. So if you look at the first part, if you look at this part here, I can take out g of x plus h. So I have g of x plus h, and then f of x plus h minus f of x divided by h. And for the second part, you can take out the f of x. So you have plus f of x and then g of x plus h minus g of x divided by h. So now if I assume that f and g are both differentiable, then I know that this limit exists. This limit also exists. If f and g are both differentiable, that's what I need now. F, g differentiable. Then I know that this limit here, this limit exists. It's the derivative of f. This limit exists. It's the derivative of g. This limit here, of course, exists because it doesn't depend on h. The limit is with respect to h. So this limit also exists. Now how about this one? This limit. The limit of g of x plus h as h tends to 0. Does it exist or not? It exists because g is differentiable. If g is differentiable, also continuous. And if g is continuous, then this limit is just g of x. Right? So if f and g are differentiable, then the limit of this exists, the limit of this exists, the limit of this exists, the limit of this exists. So I can use the limit laws. Okay. So if I use the limit laws, it's just the limit of this one, which is g of x. The limit of this one, which is the derivative of f. The limit of this one, which is just f of x. And the limit of this one, which is the derivative of g of x. So that's the right rule. It's called the product rule. So under the assumption that f and g are differentiable, we have the derivative of a product is just the derivative of f plus f of x times the derivative of g of x. That's the product rule. Okay. And the proof is already here. That's the proof. You just use the definition of the derivative and then some manipulations, and in the end you get it. The only thing you have to realize is that you have to subtract and add here something. Just that you can rearrange it, that you have really the derivative of f and the derivative of g inside. Okay. For example, if the function is x times e to the x, okay, now the derivative is by this rule. So I have to differentiate this one, which is 1. I leave this one unchanged, so it's e to the x. And I differentiate this one, which is also e to the x. So I get x plus 1 e to the x. If you, maybe once more, the second derivative. So I leave this one, I differentiate this one, which is 1 e to the x. Then now I leave this one unchanged, and I differentiate this one, which is e to the x. So it's x plus 2 e to the x. Okay, so you see the guess is that the nth derivative is what? If you look at this pattern, x plus n e to the x. This is true for all n larger or equal than 0. If you have a guess like this, in high school you certainly have learned, or I guess you have learned the method of induction. If you have a statement like this, which is true for all n, in order to prove it, you just have to show it's true for n is equal to 0. It's called the base step. And then you have to assume, assuming that it's true for n, you have to show it's true. Right, so that's called induction, mathematical induction. Mathematical induction. Of course, it's mathematical induction because it's mathematics we are talking about. The method says, okay, for n is equal to 0, you have to check it. I did it. I checked it here. It's the original function. Okay. Then you assume that it's true for n. You prove it for n plus 1. So you assume this is true. Now you want to check it for n plus 1. But that's just the derivative of the nth derivative. Okay. This one you already know. This is x plus n e to the x. So you have just to differentiate this once more. So the derivative of this one is 1 times e to the x plus okay, so it's 1 e to the x. Okay, so I assumed it's true for n. I used it here. I showed it for n plus 1. So now it's proved for all n. This method. This is one of the methods of showing that the statement holds for all n, or all n larger or equal than 0. Natural numbers usually do not include 0. So all n larger or equal than 0. You verify it for the first cases of n, and then you assume it's true for n, and you prove it for n plus 1. Any questions to this? Then again, the derivative differentiate square root of x, which we saw already before is 1 over 2 times square root of x. Then 1 minus x changed. For this one, which is minus 1. That's using the product rule. Actually, you don't really need to use the product rule. You can also just expand it. You could also just expand it first. And now, if you differentiate it once more, the product rule, this is just 1/2 x to the minus 1/2 minus 3/2 x to the 1/2. This is the same as this one if you rearrange it. You just have to multiply this out and then to this term is already this one here, and the rest is just this minus x times this and this here combined. So sometimes it's maybe not good to directly use the product rule. It's better to do some simplification of the function first before you use the product rule. So we now know how to differentiate a product of two functions. So the next logical question is, how about a quotient? So how about again, you can write down the limit. Okay, and then you can try to do similar manipulations as for the product in order to get the rule. Since we know already how to compute, you know that division is the inverse operation of multiplication. So actually, this rule should follow from the one for the product. So for instance, what you clearly have is that g of x times 1 over g of x. This is equal to 1, right? Trivial. Now I differentiate both sides. Because I don't know, this is already a quotient. It's easier than this one because f of x is 1. So this is already a quotient. I don't know this one, but I know how to differentiate the whole thing. So I can consider this. So I differentiate it, right? So you have the derivative of g of x, 1 over g of x. And then plus g of x, the derivative of 1 over g of x equal to 0. So I just solve for this one now. Right? That's already one quotient which I then which I'm able then to differentiate. So 1 over g of x. Right? You solve for this one. If you arrange it, this is what? It's minus derivative of g of x over g of x squared, right? And now this one, the product. It's just the product of f of x and 1 over g of x, which I just figured out how to differentiate. So now again I use once more the product rule. Maybe I erase this one and write it here. So now I write it once more here. So this is f of x, 1 over g of x. So again by the product rule, this is the derivative of f of x, 1 over g of x. And then plus f of x, the derivative of this one. But this I just figured out is this one. So this is minus derivative of g of x over g of x squared. And now you just slightly rewrite it. So you have g of x squared in the denominator. And then here you have the derivative of f of x, g of x, minus f of x, derivative of g of x. And that's called the quotient rule. So that's called the quotient rule. So now we also know if f and g are differentiable, then the quotient is also differentiable. And the derivative of the quotient is given by this formula. So this means we can now also differentiate rational functions, which are polynomials divided by polynomials. Because we know how to differentiate polynomials, okay, so if you have the function x minus 1 divided by x plus 1. This is a rational function now. A polynomial divided by a polynomial. Now the derivative is by the quotient rule. It's the square of the denominator, and then you have the numerator, which is a polynomial, so it's just 1 here, times the denominator minus this function unchanged, so times minus the numerator times the derivative of the denominator, which is 1. So this is 2 divided by x plus 1 squared. So if you want to know where is the tangent, so find the tangents, as before, find the tangents. Which are parallel to, for instance, x minus 2y is equal to 2. Then what you have to do is this line has slope 1/2. So what you do is you have to equate this to 1/2. So this means 4 is equal to x plus 1 squared. So this means x plus 1 is equal to plus minus 2. So x is equal to either 1 or the corresponding y values. If x is equal to 1, then the corresponding y value is 0. If x is equal to minus 3, then the corresponding y value is, this is minus 4 divided by minus 2. So 2. So there are two tangents which are parallel to this line. Namely, there are two tangents namely the first one is y is equal to, the slope is always 1/2, and then it's x minus 1 plus 0. And the second one is y is equal to 1/2, and then x minus 3, x plus 3. These are the two lines. These are the two tangents to this function which are parallel to this line. Okay, so you have to memorize this. If you haven't learned in high school the formula for the derivative of the quotient, you should memorize it. So the derivative of f of x over g of x is the derivative of f times g minus f times the derivative of g divided by g squared. You have to memorize this formula because we will use it very, very often. It will make computation of derivatives quick. I show you another example. So again, as for the product rule, sometimes you should maybe avoid using the quotient rule. If the function is the function 3x squared plus 2 times square root of x divided by x, here you could use the quotient rule. So by the quotient rule, you have to differentiate this here, which gives 6x plus, and then it's x to the minus 1/2. That's the derivative of this one. Multiplied with the denominator minus, now multiplied with the derivative of the denominator, which is 1, divided by x squared. It's actually easier here again to first simplify the function. This function is 3x plus 2x to the minus 1/2. It's easier, much easier. Now, you don't need the quotient rule for doing the differentiation. It's just 3 minus x to the minus 3/2. So you can simplify this into this expression. Because of course the result. Sometimes you probably should not directly use the rules of differentiation, so like the product rule or quotient rule. You maybe should first simplify the function and then use the rules of differentiation. There are still many functions left which we cannot differentiate unless we look at the definition of the derivative, like trigonometric functions, logarithmic functions, inverse trigonometric functions. Also, what is the derivative of a composite function? Okay. These are all topics which we are going to discuss today and next time. And eventually, once we have all the rules together, there is also another important method which is called the method of implicit differentiation. Once we have all those rules, all those methods together, we will be able to easily differentiate any kind of functions without having to evaluate limits, because the derivative actually is defined via a limit. So essentially, if you want to compute the derivative, what you need to do is you have to evaluate the limit. Okay, but these rules which we learned so far, they allow us to do differentiation without having to evaluate limits. Okay, we make a break of 10 minutes, and then I'm going to explain how to differentiate trigonometric functions.
Hello, teacher. Hello, teacher. There's no voice.
Hello，
有了。
Now you can hear me?
Yes, thank you.
Yes, because I can hear myself also. Okay, so these points are important. That's annoying. Is it? So these points here are important because here the slope of the tangent to the function is obviously 0. So here the derivative must pass through the x-axis. And then if you look at from here to here, for instance, the slope is first increasing until this point, and then it's decreasing. Okay, so the derivative must look like this here. And then here the same, the slope is first decreasing and then increasing again, and it's negative. So here must look like this. And so on. Okay, so from this picture you can easily guess what the derivative of the sine is. It should be the cosine. But let's verify this with the precise definition, with the definition of the derivative. So the derivative, our guess is if this is the sine, then this here is the cosine. That's the guess. So the derivative of the sine, by definition, it's the limit h tends to 0, and then sine of x plus h minus sine of x divided by h. So we have to evaluate this limit. Now we cannot use directly the limit laws as usual because it would be 0. It would be 0 over 0. In particular, the limit of the denominator would be equal to 0, so you are not allowed to use the limit of the quotient is the quotient of the limits. That's usually the case for the limit which is involved in the definition of derivatives. So we have to rewrite the expression. Now, the first thing which comes into mind here is, okay, sine of x plus h. You learned in I don't know, junior high school a formula for this. The sine of x plus h is the sine of x times the cosine of h plus the cosine of x times the sine of h. So maybe let's use so the limit h tends to 0. Then we have here the sine of x, sine of h, sine of x, cosine of h, plus h divided by h. Now let's rearrange this a little bit. So this is the limit h tends to 0. So we can write this as the cos, then the sine of h divided by h plus the sine of x the cosine of h minus 1 divided by h. So if we wanna compute this limit, if we wanna use the limit laws now, we have to show that this limit exists. We have to show that this limit exists. This limit of course exists. This limit of course exists because this doesn't depend on h. Note that this is the limit of the sine. This is the derivative of the sine at 0. Right? This is exactly this here. If with a limit, this is the derivative of the sine at 0. This here with the limit is the derivative of the cosine at 0. So this means that the sine is differentiable if and only if the sine is differentiable at 0 and the cosine is differentiable at 0. Then the sine is differentiable everywhere. So our guess, if you use like the pocket calculator, you immediately have the guess that this limit is equal to 1, and this limit, the other one, this limit is equal to 0. That's what we have to prove. If you know this, then you can just use limit laws, and you get here the cosine of x plus the sine of x times 0, and this is the cosine of x. So then indeed you get that the derivative of the sine is the cosine. So what is left is to prove those two relations. In particular, this I say it once more. This here shows that the derivative. This is itself a derivative of the sine, namely at 0. This is the derivative of the sine at 0. This is the derivative of the cosine at 0. Recall, we want to show that the derivative of the sine is the cosine. So we need to show that, at least what we need to show is that the derivative of the sine at 0 is 1. And the derivative of the cosine at 0 is 0. That's what we have to show. In order to show that the derivative of the sine at any x is the cosine of x. So how to show this relation and this relation? For this a right triangle, because we know we can find the sine in a right triangle. Okay, so this length here is 1. This is theta. Okay. Now we know where the sine is. The length of this one must be the sine, because the sine is the sine of theta is the length of this one divided by the length of this one. Okay. So this would be the sine. Okay. Now I extend this line until this length here is also 1. Yeah. Okay. I also plot this line here. Okay. I introduce some. So I call this A, this B, this C. Maybe I do the same note. No, I called it completely different here. So I call this O because it's the origin. I call this here C, this here A, this here B. Now you see that the length of the line from B to C, this is the sine of theta. Okay. You have here a right triangle. So certainly this is smaller than the length of the line from A to B, right? Because you just look at this right triangle here. Okay. We know that in a right triangle, the largest side, the longest side, the side with the largest length, okay, is opposite the largest angle. Here, the largest in this triangle, the largest angle is this one. So this one must be larger than this one. Okay. And certainly, the line from A to B is smaller than the arc from A to B. Right? So certainly this is smaller than the arc from A to B, which by definition is theta because of the radian measure. That's why I mentioned it. Okay. So we know already from this that the sine of theta divided by theta is smaller than 1. That's already good because we want to show that the limit is equal to 1. Now what I do is I plot here like this, and then I also extend this like this. Okay, and this I call D, and then I plot this line here, and this point I call E. There's a right angle here, as we know, because this line is tangent to the circle, so there is a right angle here. So now again, the arc from A to B. That's from here to here, going along the arc. This is certainly smaller than plus the length of the line from E to A. Okay, because it's from here to here via the arc, then going first to E and then here. Right? But the length from B to E is certainly smaller than the length from E to D. So that's smaller than the length from E to D plus E to A. But that's the length from E to A. It's this one. But what is this length here from D to A in terms of theta? Just the tangent of theta, right? Because the tangent of theta in the large triangle, the tangent of theta is this length divided by this length, but this length is 1. So this is just the tangent of theta. This here is theta. Tangent is the sine of theta divided by the cosine of theta. So if you now look at this inequality, this just means that the cosine of theta is divided by theta, right? And together with this one, we get now that the sine of theta divided by theta is larger than the cosine of theta and smaller than 1. Now you let theta go to 0. If theta goes to 0, cosine of theta goes to 1. This also goes to 1. And this one is squeezed in between. So the limit of sine of theta to this over theta, as theta tends to 0 is equal to 1. That's what I wanted to prove. So this shows the first relation. Actually, there is only one small flaw in this argument, namely, for my picture, the theta must be larger than 0. Negative theta doesn't really make sense in this picture, right? If I plot it like this. So strictly speaking, here it's the right-hand limit. But of course, this function has the same right and left-hand limit, because if you replace theta by minus theta, okay, the function doesn't change, right? Because sine of minus theta is minus sine of theta. And in the denominator, you have another minus. So this function at minus theta is the same as at theta. So of course, the limits are the same from both directions. So the left-hand limit is also 1. So the limit exists and is equal to 1. That's what I wanted to show. You see the squeezing theorem, because that's what I used here, squeezing theorem. So now I verified this one. That's okay. How about the second one? Any questions to this proof? That's probably the only proof in this the whole course where we use geometric reasoning. I don't know, in high school or junior high school, you learned a lot of geometry. Geometry is not so useful actually for calculus. Seldomly used at the university level. This one actually follows from this one. So the limit of cosine of h minus 1 divided by h. You just have to rearrange it a little bit. You multiply with cosine of h plus 1 divided by cosine of h plus 1. Why is this a good idea to do this? Because now in the sine squared of h minus 1 divided by h, and then the cosine of h plus 1. Minus the sine squared. This is minus the sine squared of h divided by h cosine of h plus 1, right? Now you write it. H tends to 0. You can take out the and then you have a sine of h over h. And then you have sine of h over cosine of h plus 1. Now I want to use the limit laws. I showed already equal to 1. Now how about this limit? This limit is even easier. Here I can use that the limit of a quotient is the quotient of the limit, because in the numerator the limit is just 0. In the denominator the limit is 2. So actually I'm allowed here, in order to compute just this single limit, I'm allowed to use that the limit of a quotient is the quotient of the limits. And the answer of this limit is 0. So this limit exists. This limit also exists. I just proved it. So I can use the limit laws. The limit of the product is the product of the limits. So this is minus the limit h tends to 0 times the limit h tends to 0 sine of h divided by cosine of h plus 1. And this limit I showed is equal to 1. And this limit It's easy to compute is equal to 0. So the whole limit is 0, as I claimed. So this one also now okay. Follows from the first one. So indeed, the derivative of the sine is the cosine. Okay, so that's the important formula. The derivative of the sine is the cosine. Okay, can I remove it? So for instance, if you have now an example like the following one, find the points where the function f of x is equal to x plus 2 times sine of x has a horizontal tangent. For this, you just have to compute the derivative, which is 1 plus
Professor, Professor, can you hear me? Excuse me. Can anyone hear me?
No, now you can hear me again?
Yes.
Yes, okay. So the derivative of the sine is the cosine. The derivative of the cosine is minus the sine. The derivative of the tangent is the secant squared. And also for the other trigonometric functions, you can easily now figure out what the derivative is. For instance, for the secant, which is 1 over the cosine, you just use the quotient rule, and you will easily see that the derivative of the secant is the secant times the tangent, and so on. You have a table. The 6 trigonometric functions are listed, and the derivatives are listed. Okay, but it's usually enough to memorize the sine and the cosine, because the rest you can derive from them. Because the tangent is just sine over cosine, cotangent is cosine over sine, secant is 1 over cosine, cosecant is 1 over sine. So you only need to know the derivative of the sine and the cosine. Here's a final example. How about the 2 times sine of x times cosine of x? Now, for the derivative, you can use the product rule. So it's 2 times. The derivative of the sine is the cosine times the cosine, so cosine squared. And then minus 2 times. Now the derivative of the cosine, which is minus the sine, so it's minus sine squared of x. You maybe know this is equal to 2 times. You also know that this is the sine of 2x, right? So the question is it not possible to differentiate this directly to get this one? But for this is a composite function, right? So if you have the function, you can look at this as a composite function, where g of, maybe I write it with u and all this capital F, just a, I call, you have a function f of u, which is the sine of u, and you have a function g of x, which is 2x. So this is actually then the composite function of f and g, right? You have a function which is, you have an inner function which is 2x and the outer function which is the sine. So actually, here you naturally have a question which is how to find the derivative of composite function if you know the derivative of f and the derivative of g. Okay, so the question I want to ask is, if you have a composite function, what is the derivative? This is easy. The rule is easy to figure out if you think about. So I call this maybe u, this y, and this u. Okay. So in Leibniz notation, what I want to do is I wanna find the derivative of y with respect to x. I go from x to u, and then from u to y, right? I want to know what is the derivative of y with respect to x without the middle step u, in terms of the middle step u. If you think about it, it's easy to guess what the rule should be, because if you think about this as a two-step process, and you think about this as rate of changes. Okay, so just to take any example, let's say a farm is producing milk. Okay, so u is the milk, x is time. Okay, and then the milk is the milk is sent to a company, and the company turns the milk into cheese. Okay, so that's the second function. Milk, output is cheese. Here the input is time, output is milk. Okay. Now if the farm doubles the production of milk, and the company which produces cheese triples the production of cheese, what is then the rate of change of the output of cheese over time? It gets multiplied by a factor of 6, right? Because if over time the farm is doubling the output of milk, and the company, given the amount of milk, can triple the amount of cheese it produces, okay, then the amount of cheese over time, the rate of change of the amount of cheese has to be multiplied by 6. Right? So that's clear. The rate of changes have to multiply. So what you expect is this derivative should be what? It should be the derivative of u with respect to x multiplied with the derivative of y with respect to u. That's what I just explained. Of course, you can. If you look at this as a fraction, I told you this is not a fraction. But if you look at this as a fraction, you say, of course, this is true, right? I just erased this one. It's equal to this one. But these are not fractions. Also, if you think about them as rate of changes, of this is the clear guess. This must hold. Or in terms, if I write it like this, then this means. So that's Newton notation. Then this means it's the derivative of f evaluated at g of x times the derivative of g of x. That's what this meaning is. Okay, that's indeed true. That's called the chain rule. So if f is differentiable and g is differentiable, then the composite function is also differentiable. And the derivative of the composite function is given like this. So for this example, so what you have to do is you have an outer function. F is the outer function. G is the inner function. Right? So sine is the outer function. This is the inner function. You have to differentiate the outer function and evaluate it at the inner function, which is left unchanged. And you have to multiply with the derivative of the inner function. You differentiate the outer function, which is the cosine. Evaluate at the inner function, 2x. Multiply it with the derivative of the inner function, which is 2. Okay, so it's the same result here. By the chain rule. Okay, I maybe write it down as a theorem. So the assumption is again that f and g are differentiable. Then the derivative g multiplied with the derivative of g. Okay, so that's what I just wrote here. So why is this? Maybe I show you a proof, which is not really a proof, so I put it under quotes. Not really a proof. Okay. In Leibniz notation, this means dy over dx is equal to dy over du over dx. Right first. Du over dx times dy over du, where u is g of x and y is f of u. That's in Leibniz notation. So why is this true? Because you can say du over dx. This was delta x tends to 0 of delta y over delta x, where delta y is what? Delta y is f of x plus delta x. I don't know. F of u. F of it's here. X plus delta x minus f of g of x. You can say delta u of x plus delta x minus g of x. That's the change. Replace x by x plus delta x. Okay, so actually you can write this as the limit to 0 note that if delta x tends to 0, then delta, that's because the function g is assumed to be differentiable, so it's also continuous. So if you consider the limit here, delta x tends to 0, x is fixed. This will be equal to 0. So by assumption, this limit, if delta x tends to 0, goes to 0. This limit, as delta x tends to 0, also not goes to 0. This limit goes to the derivative of u with respect to x. This limit goes to the derivative of y. Okay. So by the delta y over delta u times the x. And in the first case, delta x tends to 0 by delta u delta u times limit delta x tends to 0 of delta u over delta x. And the first of y with respect to x. That's just by definition. This is what I wanted to prove, right? It's the chain rule. So why did I put it under quotes? Because the proof is wrong. There is one step which is wrong here. I don't know in high school. You learned the chain rule in high school? It's sometimes it's taught in high school, and sometimes even some high school textbooks, they even have a proof of the chain rule, which is this one, the wrong one, without saying it's wrong. So who can tell me which step is wrong? Which step? It's not completely wrong. It's not entirely correct. Which step? This is certainly correct, right? Because this is just a. Now this here, I explained that we are allowed to do this. I can split the limit. The limit of a product is the product of the limits because of the assumption f and g are differentiable. So that's okay here. This step is okay. Delta x tends to 0 implies that delta y also tends to 0. So this is okay. This is the same limit. And from here to here, just definition again. So the only step which might be wrong is from here to here. Delta x not, because delta x tends to 0. So the limit means delta x goes to 0, but it's never equal to 0. But you are right. The delta u could be 0. Right? Just think about if the function g is a constant function, for instance 1, then of course this is 0. So this delta u could be 0. So you're not allowed to divide by 0. That's the problem. So this step here is usually wrong. But of course, for many functions, this might be true. This step. So this is not a precise proof. It explains you, but it explains you in many cases why this is true. Next time I will show you the precise proof. Okay. The trick of the precise proof is not to write things as fraction, because if you avoid writing things as fractions, okay, you are not dividing by 0. That's easy. But so, of course, at some stage you have to write a fraction because of this definition. Okay, but you do this at the very last step. At the very last step, you divide by delta x, which you are allowed to do because delta x is never equal to 0. So that's the idea of the proof. I'm showing you the proof next time. Maybe today. Let's look at some examples. since you haven't, maybe most of you haven't learned the chain, just to see how it applies. It's actually, once you have done a couple of examples, it's quite easy to use. So for instance, let's say sine of x squared. You only have to think about, there is an inner function g and the outer function f, right? You have to first figure out which one is which. So here the outer function is the sine. The inner function is x squared. Okay, and then it's always the same. You have to differentiate the outer function at the inner function, which you leave unchanged, and then you multiply with the derivative of the inner function. So here the sine, the inner function is x squared. So you differentiate the outer function, which is the cosine. The inner function you do nothing, you just copy it. And then you multiply with the derivative squared, which is 2x. Right? And then square like this. Now, inner function and outer function change their role. The outer function is now x squared. The inner function is the sine of x. So you differentiate the outer function. You differentiate the outer function, which is x squared. The derivative of x squared is 2x. You evaluate it at the inner function, so it's 2 times sine of x. And then you multiply with the derivative of the inner function, which is the cosine of x, because the derivative of sine of x is cosine of x. More examples. So for instance, how about x to the cube minus 1 to the 100? How about this one? What is the outer function? The outer function is so the function f of u is u to the 100. The inner function g is what is inside this function? X to the cube minus 1. So it's the derivative of the outer function, which is 100 u to the 99. But for u, again, you have to replace it by the inner function. And then you have to multiply with the derivative of the inner function, so the derivative of this function, which is 3x squared. More examples. So how about g of x is equal to x minus 2? How about the inner function is a rational function? The outer function is u to the 9. U is by 2x plus 1. So this. Okay. The derivative of the outer function is 9 times x minus 2 divided by 2x plus 1 to the 8, because the inner function doesn't change. Multiplied with the derivative of the inner function. So the derivative of this one. For this you have to use the quotient rule. So it's 2x plus 1 squared. The derivative 1 times 2x. This function x minus 2 times the derivative of this function, which is 2x 2. Okay, you can simplify it. Here's another function. So how about function is e to the u. The inner function is u is sine of x. So the derivative function e to the u. So it's e to the sine of x multiplied with the derivative of the inner function, which is the cosine of x. This actually also allows us to differentiate a to the x. Because a to the x you can write as e to the ln of a. That's a constant times x. Right? So the derivative, the outer function is e to the u. The inner function is ln of a times x. So it's e to the ln of a times x times the derivative of the inner function. So this is a to the x ln of a. So you see, I started today's lecture with, that was one of the things I started with, the derivative of exponential functions. And I said only a is equal, e to the x we can differentiate by definition. Now we can also differentiate a to the x. And the constant which I couldn't identify at the beginning of the lecture, now I know it's ln of a. That's why for a is 0.69, because that's ln of 2. And 2, because then this is only for e to the x, the derivative is the okay. Any questions to the I show you also how to prove this next time, because we will need the proof. We will need some of the key ideas of the proof next semester. Questions? If not, then that's it.
OK， 你们听得到我声音吗？好，可以。那个，我们明天 ，OK， 我们的时间是6点到8点。07教室 ，OK。你们都听得到吗？可以，好，谢谢。我们那个 TA 课明天6点到8点 ，OK， 260、207以后都是这个时间了 ，OK。260是在商馆，这里是250，正图书馆对面那个。怎么了？哦，好，就这样。你们那个考试有问题的要来找我哦。
两个。